Welcome. In this video, we are going to talk about what happens when two atoms come together and bond. And the type of bond that will form depends on what types of atoms are bonding. And when we're thinking about this in terms of bonding, the categorization that tends to be very useful is it a metal or is it a non-metal? And the metals are over here on the left-hand side of the periodic table. The non-metals are over here on the right. If we think about what we know about our periodic trends, the metals have really low effective nuclear charges. Their electrons, look down here on this bottom left, they've got a larger number of shells. So as a result, they have a weaker attraction for their valence electrons. Over here with your nonmetals, they've got a relatively strong attraction for their valence electrons. They've got high effective nuclear charges. So that gives them a strong attraction. All right. And when you combine a metal and a nonmetal, the metals have a weak attraction for the electrons, nonmetals have a strong attraction. So electrons will be transferred from the metal to the nonmetal. And that's what happens in an ionic bond. Electrons are transferred between atoms. And that's what creates those things called ions. In a covalent bond, that's when you have two or more nonmetals. Covalent bonding involves the sharing of electrons. So in covalent bonding, we share. In metallic bonding, this occurs in metals, and our metals, remember, all have a very loose grip on their electrons, and what happens as a result is the electrons are pooled between atoms. We sometimes see this referred to as the electron sea model. Another term I've seen used to describe it is that the electrons are delocalized, meaning they're not tied down in any one spot. They can move around freely around your sample. So here's a visual showing what's going on with these different types of bonding. In your ionic bonding, you have a metal with a really, low ionization energy. Non-metal, it's got a really strong attraction for the electrons. The metal is going to transfer electrons to the non-metal. So it's going to give up an electron. As a result, you have positive and negative ions. And then opposites attract. They form this structure right here, which we call a crystal lattice. Looking over here at covalent bonding, this is when you have a group of nonmetals. They all have really strong attractions for their electrons, so the atoms are going to share electrons. So no one really wants to give up their electrons, they're just going to share. In metallic bonding, you've got a group of metals, they all have a weak attraction for their electrons. They kind of pool their electrons together and everyone shares them, and they're delocalized. They can move anywhere around this solid. That's what allows metals to conduct electricity well. Network covalent, notice how that wasn't really maybe represented in here. Network covalent, it's covalent bonding because your atoms are sharing electrons. But what's different about them is we don't form molecules. What we have here is we have this one really big network, like a big grid of atoms where each atom's covalently bonded to all the atoms around it. This gives network covalent substances very high melting points, makes them very hard. Some classic examples of that would be a diamond is an example of network covalent bonding. Diamond is just pure carbon, but they're in this rigid grid there. And then another common one would be silicon dioxide, and it looks like this. I think our silicon is in gray and the oxygens are in red in this picture, just so you know. You can see how in this case, every atom is covalently bonded to the atoms around it. Which is a little different than in water, which this is an example of molecular covalent bonding, where what you have here is you have water molecules where the H's and, these H's and the O's share electrons, but these waters are not bonded to each other. So we just have, these would be examples of molecules. Versus in a network covalent, there are no individual molecules. Everyone's bonded to everyone else. And some network covalent substances you should know would be diamond, graphite, pure silicon, and then silicon dioxide. So with the network covalent, this is an example of things you just kind of need to memorize these common examples. Silicates form about 90% of the Earth's crust. So it might seem like, there's not very many network covalent substances out there, but like in terms of number of types of them, but they're a very important, class of materials to know about because there's lots of them in the world, right? Okay, so something else to think about in terms of bond types is electronegativity. We want to be able to use electronegativity to talk about what type of bonding is going on. The definition of electronegativity is it's the ability of an atom to attract electrons to itself in a chemical bond. And here's a periodic table. You can see there's a periodic trend for electronegativity that looks really similar as ionization energy, right? Because over here on the top right, we've got high electronegativities, just like we have high ionization energies. Down here in the bottom left, we've got low electronegativities. So fluorine has a really strong attraction to electrons. Down here, francium, cesium, they have really weak attraction for those electrons. The electronegativity, it's a scale, it's a 0 to 4 scale, with kind of 4 being the highest, 0 being the smallest. There's no unit associated with this. This doesn't represent like a kilojoule or anything. It's just a relative ranking here. And the electronegativity of the atoms involved is what's really determining the bond type. So we say ionic bonding occurs when you have a metal and a non-metal together. That's because your metals have really low electronegativities, your nonmetals have really high electronegativities. So when you put them together, there's a really big difference in electronegativity. The metal will give up its electrons to the nonmetal. That's form ionic bond. At the other extreme, if the electronegativity difference is 0, so if they've got like the same electronegativities, then they're going to equal attraction on the electrons. So they're going to share those electrons equally. And that's what we call a non-polar covalent bond. But there's something in between where they're sharing electrons, so it's not quite ionic, but it's not quite non-polar. So they're sharing electrons, but they're not sharing them evenly. And that's something called a polar covalent bond. That's when there's an intermediate difference in electronegativity. So it's not big enough to be an ionic bond, but if they're not sharing them evenly, that's in between. We call that polar. And as a result of that uneven sharing, you notice that in this visual, you can see that one side of the bond has a slight negative charge, the other side has a slight positive charge. That's due to that uneven sharing. So there's more electrons on this side, so it's got a slight negative charge, less over here, it's got a slight positive charge. Here is a visual, if you might remember from regular chemistry, you may have seen this comic strip that I like, thinking about bond types and polarity. So in this comic, you might remember we're using ice cream to represent electrons that are being shared. And in the example of non-polar covalent, the two atoms sharing the ice cream, the electrons, have equal attraction for those electrons. So they're sharing them equally. And that's what we see here in this picture, the two penguins and the two polar bears. Non-polar covalent, this is a combination we had a penguin and a polar bear. So my polar bear represents an atom that has a much stronger pull on those electrons. So in this case, my polar bear represents fluorine, which is really high electronegativity, and my polar bear, is pulling the electrons away from my penguin. So notice how the electrons are still being shared, like they both have a grip on the electrons, but really the polar bear is getting way more of the ice cream than the penguin. And as a result, since the electrons are being pulled more towards this side, the fluorine side of the bond ends up with a slight negative charge, the hydrogen side ends up with a slight positive charge. And that's what it means to be polar, is when it's, uneven and you end up with a positive and negative sides to the bond. And we'll get into this more with molecular bonding and identifying molecules that are polar. And then the other extreme then here would be ionic. So if the one atom is so much more electronegative than the other, it's going to be strong enough to just tear the electron away, and that's when you form ions. So in this case, notice the electrons are not being shared. The polar bear is hogging it for himself. The poor penguin's like, oh no, and that's where he formed ions. So here's an overview, again, thinking back to all the different types of bonding. When both atoms have really low electronegativity, they're all metals, you form metallic bonding. And within metallic, you can have a pure metal or you can have an alloy, which is a mixture of metals. If you combine a metal and a non-metal, you have ionic bonding. And if you have two nonmetals, you've got covalent bonding. And covalent means they're sharing electrons. You can have molecular covalent or network covalent. And we should actually add a level here. Within molecular covalent, you can be polar or you can be non-polar. And here's another overview of the different types of bonding. And it's within molecular solids that you can be polar or non-polar. But otherwise, the main categories are metallic, ionic, molecular, and network covalent. So that's an overview of bond types. Let me know what questions you have to follow up.